Namaskar, welcome back. So this was our last slide where we discussed about the importance of active tectonics, and we also had discussion on the moderate size earthquakes if they are triggered or produced in a populated area, then that can cause catastrophe. And everything depends on the buildings which are been built using the proper building codes and all that. And nevertheless, if the area is located even though away from the area that is what we usually call the epicentral zone, then also those areas will be affected provided they are having appropriate site conditions. That means if they are having loose material and water saturated material, then those areas will be affected, and that what we call the process of liquefaction. That is also a secondary process. Now, further, if we move and talk about that, what are the type of information we collect and what is the output of that, why we need this information is straightforward. Okay, we use this like we are talking about the scale of work, and that we have discussed that we will come from the global to regional to site specific, that is local and then site specific, and the data input is required we collect in on surface, and what type of data has been collected, that we will soon see about that. And finally, this has been the data has been used for societal importance, okay, societal use. So mainly to reduce the risk factor and all that. So what we do on the regional scale, that is the measurements, observations from topographic maps, aerial photographs. So we are still doing on the regional scale. We try to collect the geological maps and all that of that area. We also try to understand based on the historical data, and then understand the relative tectonic activities of the areas, and that will be used for regional planning. Okay. Then we try to collect the data of the landforms. We measure the landforms in the field. We try to get the age of those landforms. Okay, so we produce the chronology of those landforms and try to reconstruct the tectonic history. Okay, then we also talk about that what is the rate of faulting uh, along that weak zone, and recurrence interval of an earthquake, what is the uplift rate. So there are lot many parameters on which we work in field, and before heading to field we do in lab actually. So as there are few very important points that we use this aerial photographs, high resolution aerial photographs we do to identify the tectonic landforms. And before this, we try to look on a global scale and the regional scale, what is the tectonic setup. For example, for Himalaya, if you have to talk about, then Himalaya is what sort of deformation we are having in Himalaya, what type of faulting can be expected in from that region. Okay, so if there is a compressional tectonic environment, we expect that most of the faults or the deformation will be in terms of the folds, and the fractures or the cracks which will show the displacement, that what we call faults, will be mostly the reverse and thrust faults. Okay, so that part you will learn as we move slowly, but this is a regional picture which talks about that why we collect the data and what is the end product and deliverables. Okay, so we do that, and then finally this has been used for regional planning on the, and then we also incorporate the site specific studies, establish building codes. Okay, based on this. Okay, and the main aim is the earthquake hazard reduction. Okay, so we try to reduce the if we know that what magnitude earthquake is going to trigger, what amount of ground shaking will be resulted from that earthquake, and accordingly the structural engineers will take up the studies and geotechnical engineers to develop the building codes. Now, understanding earthquake, this is the tagline I would say, that efforts to minimize hazard and risk. Okay, so assessment of earthquake hazard at a particular site includes identification of tectonic framework. This what we were talking about, that we go on the global scale, then narrow down to regional, then local, and then site specific. Okay. So when we come down to the local and site specific, and even at regional, we try to understand that what will be the expected geometry of the fault and what is the geometry of the fault at that particular site. That is important for the understanding the earthquake process, as well as how we can understand the overall earthquake sequence in that, and what will be the magnitude and all that. Okay. So we also talk about that what is the pattern of the fault. Okay. Whether the fault remains with the same pattern along the strike, or where it has been oriented, or it changes its pattern. Okay. So that is also important. Then seismic source, how deep earthquakes are expected to occur, if there is a shallow earthquakes or deep earthquakes or intermediate earthquake or close to the surface. Okay, how close to the surface are not many. You will see even at 10 kilometers we consider as shallow earthquakes. So mostly the earthquakes in Himalayas, which ranges from 30 kilometers or go up to 70 kilometers or so. Like Bhuj earthquake was, if I am not wrong, was of at around uh, 30 or 40 kilometers. Okay, if maybe I'll just I right now don't remember exactly, but we will try to tell you about that. So shallow earthquakes are more dangerous actually. Okay, in the sense of we are talking about in terms of the damage. Okay, then we also try to understand that what is will be the expected magnitude at that particular site. Okay, and then what will be the recurrence interval. So this part we discussed in previous lectures also. Okay, briefly, but we'll talk in detail when we are talking about the magnitudes and what is the seismic source, how deep. Okay, but if, for example, if you take that, suppose this is your surface and there is a fault line over here. So, and that fault moves some like in section, it looks something like this. Okay, so mainly the idea behind this is that you need to know that what is the depth at which the earthquake will trigger, and this will be your epicenter on the surface. Okay, so the depth plays an important role because of its in releasing energy and the amount of damage it can result to that location. Okay, then the part, if you look at on this, that why we are so much keen in understanding the earthquake process, as I have been emphasizing that we may be located far away. Okay, from the, for example, if you, this is in Himalaya here, and then we are located far and we are having an urban settlements. Okay, but what is the local ground condition over there? Okay, if you are sitting on a hard rock, the effect of the seismic wave which is propagating under the surface of the earth or along the surface of the earth will have different amplification. Okay, and that results into your damage pattern. So how far we are located and at what depth. So this is the type of the part which we were talking about, that we talk about the depth, that is the source of the point where the energy will be released. Okay, stored energy will be released, and how far we are sitting and what type of buildings are there, what type of material on which those buildings are been constructed. Okay, so first most is the tectonic framework we need to understand, that is the geometry and the conceptual variability of the fault present in that area. So how the fault, probably the, if it is a normal fault, reverse fault. So this terminologies which I am using here will come across. Okay, so one is your reverse fault, another type is your normal faults, and third is your strike slip. Now this is the terminologies of given to the fault, And if you just define the fault, so it says that any fracture, for example, if you are having this sediments and any fracture is there, and if this fracture is showing some sort of a displacement, okay. So, for example, we are having this unit here, the same unit is on this other side, this is the fault, this one is the fault, and then if this unit has been displaced, then we say this as a fault. But faults may be secondary faults also, and they may be seismogenic faults which are having potential to trigger earthquake. We are interested in the earth faults which are capable of producing earthquake and which have triggered earthquake in the past. Okay. So, faulting for us is very important, and then what type of mechanism, because this three faulting pattern will be seen in a different way, mechanism. Okay. The one is if you are talking about the reverse fault, then mostly those reverse faults are seen in the compressional tectonic environment, okay, where the two plates are colliding each other, or then there is a compression. Okay. So, along the weak zone, the wall, the block will move up. Okay. But in terms of the normal faulting, the blocks will move down, okay, because there is an extension which is going on. So, one is compression, the block is going up because of the squeezing up of the material, and in one there is an extension where the blocks move down. Okay. Third one is along the strike. Okay. So, this is the strike of the fault, that is an orientation of the fault. So, they will move horizontally. So, you have reverse slip, you have normal slip, and you have strike slip. Okay. And you may have the combination of this two also, either it is like strike slip and normal, or strike slip and reverse. Okay. So, that what has been the second point we are looking at, and that need to be focused on, is the focal mechanism. Okay. So, what are the focal mechanisms? We'll talk when we are talking about the seismic waves and all that. But introductory part, if we see, you should know that there are three type of fault movements or the faulting pattern. One is strike slip, normal, and reverse. Okay. So, we also should know that what type of faults are present in our neighborhood. Okay. And the energy released, at what depth the earthquake is likely to occur. Okay. Because that is going to affect in terms of the intensity of ground shaking. Then we are talking about the seismic wave propagation or radiation and propagation. Okay. So, how far the seismic waves will affect. Okay. Then influence of local soil condition. As I told that if you are having the loose material, okay, and that what you call unconsolidated material. Okay. Now, this unconsolidated material is very common if you go to the Indo-Gangetic plain. Okay. And that is what we call the alluvial plain. And this alluvial plain is comprised of your unconsolidated material, and this unconsolidated material have tendency to amplify the seismic waves. Okay. So, depending on the local soil condition, the amplitude may increase of seismic waves. And if you are talking about the increase in amplitude, then this is the areas are going to have more ground acceleration. Okay. So, finally, if with all these parameters, one can talk about the hazard assessment. And we can say, because it is associated with the process of earthquake, then you can say that this is what we are talking about, the earthquake hazard assessment. This has also been termed as seismic hazard assessment, SHA. So, if you know all these parameters, you know the site conditions, you know that how far you are located, what is the type of earthquake, what will be the magnitude of the earthquake, then you can have proper seismic hazard assessment. Now, earlier when this like the science part of the paleoseismology, okay, paleoseismology basically is the term which has been used for understanding the ancient earthquakes, okay, and then we also call earthquake geology, okay. So when it started and slowly it evolved and people came up with new data and then had more and more understanding on this process, okay, of the earthquake recurrence. So initially it was like that earthquake is very systematic process, okay, and that systematic process depends on the storing of this energy which has been given by, or maybe they resulted by the plate movements, okay. Either the plate is colliding, either the plate is subducting below or passing past each other, and that was like it will depend on the strength of the rock, because what is the strength of that rock or the material to withhold with that energy, okay. But finally after the threshold limit it will slip or it will break, okay, it will crack. Similarly, if you take some string ting, like what we can say string you can take, or maybe you can take the pencil and try to bend it, that wooden part will initially bend and finally it will break, okay. Now the the point which I was trying to explain here is that initially we thought that this process is very periodical, very systematic, and over the time this energy has been stored, that is the stress is building up, okay. So what it says, the stress builds as tectonic forces deform the rocks on either side of the locked fault, okay. So the locked fault means they are talking about that this is the plane here, and then when the energy has been getting stored, okay, so there is a pressure which has been building up here and that has been stored, okay. So locked means not no movement here, so it is locked, okay. But as soon as this threshold limit has been crossed, that is your rock strength, okay, it will slip. So this is the, and that what the event that you will come across will be your earthquake, which has been shown here, okay, with the red line. So this is the time when the energy has been released, and over this period the energy has been stored, okay, and here this is the time when the energy is released, and that is your earthquake. Again on the same fault the energy will be stored for this much amount of time and then it will be released here. So one can have a sort of a very systematic time span of the similar type of earthquake. So it says what we were talking about, that when the stress exceeds the strength of the rock, that is the threshold limit, then it will slip, okay. Now if you are having this number of earthquakes which are occurring at the same interval of time, then we can easily predict that next one will be here, okay. So this will be the slip over here, okay. So if you have, say, the scale of here, you are having the 10, then you are having like 20 here, then you are having 40 here. So you can say that, okay, fine, at 50 years you will have another earthquake, okay, you can predict that, okay. But the question was that this may not be the case in reality, okay. In real sense, when we started working on, then we found that the recurrence of the earthquakes are not same, and every time on the same fault, not this, we don't expect to have the same magnitude earthquake. Sometimes the magnitude may be around 8, Okay. Sometime it will be around 7 or 7.5. This is just an example. Okay. So, what we started looking at, that if this particular fault or the plate boundary is having a capability to trigger the magnitude of earthquake of 8, okay, but did not trigger that, and it triggered almost like in half year. Okay. So, that means that the incomplete stress was released. Okay. Then chances are there. So, ideally, if we say that this was the time span which it should have taken to trigger another earthquake, then this was exactly the time when the same earthquake would have triggered. Okay. But that was not the case. It did not trigger the same magnitude earthquake because the slip is less. Okay. So, incomplete stress has been released here. So, what will happen is that chances are there that again the stress will build up, but it will now release because there is a stress which has been left out, and more stress will develop and it will release the stress here. Okay. So, what we are having, the cycle is cycle is disturbed. Okay. It is not the same as we were looking at in this a typical hacksaw blade type earthquake which are occurring. Okay. So, these are the notches here, but this is not seen in this pattern. Okay. The second example which it shows is that the change in stress from earthquake from the nearby source. Okay. So, possibilities are high that the nearby earthquakes which have been triggered on particular fault may trigger the stress release on the near another fault. Okay. So, change in the stress from earthquakes on nearby fault, and that is what we call the process of triggered stress. Okay. Because there are multiple lines which are under pressure or stress is building up here. Okay. So, if this has triggered the earthquake, it might trigger the earthquake on this in the next shorter period. Okay. And then what has been realized is that over the time which again and again this rocks are been displaced, they are weakened in terms of holding their strength, or the strength has been weakened. Okay. So, somewhere the change in the strength of the rocks will be seen. So, it may not be able to hold that much of energy, and it will very in short periods you will see an earthquake. Okay. So, that is again another part which we have come across, that older earthquakes were having a larger uh, time span between them, that is the recurrence interval, but the younger ones, okay, the recent earthquakes were showing that they have occurred, the slip took place in a very short interval of time. Okay. So, shorter interval has been seen here. Okay. So, more number of earthquakes in shorter intervals. Okay. So, earlier what we were looking at here is that you have this much of length or the time span which did not match here. Okay. Maybe this is there, but this is again and shorter, and with the shorter interval you have another earthquake here. Okay. So, everything has been now depending on the strength of the material. Okay. So, this is another way to look at the recurrence interval. So, we may not have the similar recurrence interval in given particular area. Okay. Then of course, as we were discussing that we are very keen in having that what is the surrounding geology and what are the structures which are present, active structures close to any important structures. Okay. So, structure, that is civil structure. For example, here we are looking at a dam, and this area has been mapped in detail, which shows that there is an strike slip fault here, and then we are having the thrust fault over here with an upside. This one is upside up and this is down. Okay. and then you have the geology in this. Okay, so there are three types of material which has been seen here. One is igneous rocks, which are harder. Then sedimentary rocks are also harder, but it can result into the liquefaction if they are very soft. But alluvium is going to affect the structure. Okay, so I'll stop here and we'll continue in the next lecture. Thank you so much. Namaskar.